Welcome back, Focus Learners, and let's get right into today's explainer. Today, we're looking at a material of absolutely incredible extremes. We're talking about a substance so full of paradoxes that it literally spans the realms of high-end luxury jewelry, deep space exploration, and the very core of atomic energy. So get ready, because we are unpacking the wild story of beryllium.
Okay, let's dive into this. I want you to picture something for a second. On the surface, what could possibly connect the lush, beautiful green emeralds that the ancient Roman Emperor Nero famously used to watch gladiatorial games with the terrifying extreme heat of a nuclear reactor meltdown? I mean, it seems like a massive leap, right? One represents ancient luxury, while the other is one of the most hostile, volatile environments ever engineered by humankind.
Well, the answer bridging that massive gap is element number 4 on the periodic table, beryllium. And here's a crazy fact for you. When the universe was formed, the Big Bang only managed to produce hydrogen, helium, and a little bit of lithium. It completely skipped over beryllium. Instead, this incredibly rare, silvery white metal is only forged in the intense, catastrophic death of a star, a supernova.
Which brings us to Section 1. Meet beryllium, from supernovas to spark-proof tools.
Let's get properly acquainted with this cosmic underdog and see how it found its way out of the stars and into our modern industries. Beryllium was first discovered way back in 1798 by the French chemist Nicolas Louis Vauquelin. And today, while it is the magic ingredient in stunning beryl minerals like emeralds and aquamarines, commercially it's mostly extracted from bertrandite ores. Why do we want it? Because it's lightweight, incredibly strong, and boasts remarkable electrical and thermal conductivity. We actually mix it with copper or nickel to create crucial structural materials for high-speed aircraft, missiles, and even spark-proof tools, which, as you can imagine, are absolutely essential for safety in highly flammable places like oil refineries.
Moving right along to Section 2, a nuclear superpower, the magic of BO.
And this brilliantly illustrates what happens when beryllium bonds with oxygen, becoming beryllium oxide, or BO. This is where the real magic happens. This material has the highest thermal conductivity of any metal oxide out there. It acts like an absolute champion at pulling heat away from where you don't want it. Pair that with a staggering melting point of 2,570 degrees Celsius, and you've got a material that can withstand the fiercest nuclear reactor environments. Plus, it is an exceptional neutron moderator and reflector. That means it slows down and bounces neutrons right back into the reactor core, which keeps the nuclear chain reaction going highly efficiently.
But it hasn't all been smooth sailing. Section 3, Historical Reactor Projects, the Dark Side and Doomed Trials.
The journey to actually harness this power has been, frankly, pretty brutal. During the atomic age, engineers absolutely raced to use beryllium, but they quickly realized that taming this element was a massive headache of engineering and safety hurdles. Just take a look at this timeline of ambitious, mid-century projects that ultimately crashed and burned. In 1945, the Daniels reactor proposed using BO, but a lack of experimental data killed it. In 1954, Oak Ridge National Lab actually ran the aircraft reactor experiment using a BO moderator, but it only managed to operate for 10 days. Then, in 1957, the Pluto project tried using BO in a nuclear ramjet engine for missiles, but thermal stress, vapor reactions, and the invention of better radar tech got that one canceled too. Finally, the experimental beryllium oxide reactor in 1958 was built to test a gas-cooled system, but they abandoned it before it ever even achieved criticality.
And beyond those engineering failures, there is a very real human cost to beryllium. Looking at the EPA document on this slide, you immediately see the strict regulations required for processing this material and managing its waste. Why? Because the metal and its dust are highly toxic. If a worker inhales beryllium dust, it causes an incurable chronic lung inflammation known as berylliosis. This severe health risk is just a massive shadow hanging over the material, demanding incredibly strict and very costly manufacturing safeguards.
So when you weigh it against the alternatives, the engineering trade-offs become pretty stark. Just check out this comparison on the slide with standard reactor graphite. Graphite is cheap, we know how it works, but it requires a much larger reactor core and poses very real flammability risks in an accident. BO, on the other hand, it lets you build a highly compact core and boasts totally superior heat management. The catch? The cost per gram of fissile material in a BO system is literally 15 times higher than that of a graphite system.
Which perfectly sets up Section 4, the fuel of the future, the super spice of nuclear reactors.
Because despite that dark history and the crazy price tag, modern science hasn't given up on BO. Welcome to the redemption arc of beryllium oxide. Right now, it's being tested as a next-generation, accident-tolerant fuel. But instead of trying to build a whole reactor core out of it like they did in the 50s, scientists have developed a UO2BO composite fuel. Think of beryllium oxide as a kind of super spice. By infusing standard uranium dioxide fuel pellets with just a tiny percentage of BO, engineers can fundamentally transform the fuel's thermal properties, allowing it to burn significantly cooler and much safer.
Now, what's really interesting about this slide is the sheer scale of the improvement we're talking about. Look at this. By adding a mere 10% by volume of beryllium oxide to standard nuclear fuel, the thermal conductivity literally doubles. That is a 100% improvement. That means heat escapes the fuel pellet and transfers to the coolant twice as efficiently as before.
And the knock-on effects of that improved heat transfer? They're huge. It lowers the fuel's internal temperature by hundreds of degrees. And because the fuel is cooler, it dramatically reduces the buildup of those dangerous fission gases that normally stress the metal clotting. This drastically increases the overall safety margins of the reactor if an accident were to happen. Plus, as a great little bonus, the enhanced efficiency even extends the operational life and energy output of the fuel cycle.
Okay, time for a reality check in Section 5. The catch: challenges ahead for beryllium.
Because, there is no such thing as a free lunch in nuclear physics. There are still major technical hurdles scientists have to overcome to make this incredibly promising fuel a commercial reality. So, the crucial point is that we have 3 massive steps ahead of us. Step 1, the economics. We have to figure out how to mitigate manufacturing costs that are, as we saw, 15 times higher than current standards. Step 2, the chemistry. We have to engineer solutions to prevent BEO from reacting poorly with water vapor at extremely high temperatures, specifically above 250 degrees Celsius. And step 3, human safety. We absolutely must implement and maintain strict manufacturing safeguards to protect our workers from berylliosis during fuel production and recycling. But there is a very bright light at the end of this tunnel. In 2018, NASA announced the highly successful test of their kilopower space reactor. This 5-kilowatt prototype utilized a beryllium oxide reflector and heat pipes perfectly to survive simulated deep space conditions and power failures. It proved that in the most extreme, demanding environments imaginable, BO's modern potential is entirely real and highly reliable.
As the source text states, the successful test of kilopower is only a first step toward harnessing fission power in space. Look, beryllium is a dangerous, incredibly expensive, and stubborn element to tame, but it also holds the key to fundamentally safer reactors here on Earth and limitless exploration out there in the cosmos. So I'll leave you with this question to ponder. Are the astronomical costs and strict safety risks of element number 4 worth the ultimate reward of a safer, limitless energy future? Think about it. Thanks for joining us, and we'll see you in the next explainer.